Hello dear students, in this class I am going to discuss about the electric potential energy due to the system of point charges. In the last class we have discussed about the relation between electric potential and electric field and difference between the electric field intensity and electric potential. In this class we will discuss about the electrostatic potential energy. Electrostatic potential energy of a system of point charges. Electrostatic potential energy of a system of point charges. Potential energy means energy possessed by the body due to its position is called potential energy. But in this case, in case of electric potential, when a charge moves from one point to another point, or the amount of work done is required moves when a point charge is moved from one point to another point, that work done is stored as electric potential energy. Here, electrostatic potential energy. Electrostatic potential energy, it means the amount of work done in bringing a point charges to their respective locations from infinity, or the amount of work done is required to bring a unit charge from infinity to their respective locations is called electrostatic potential energy. Now, we will discuss this in different cases, in the presence of electric field and in the absence of electric field. Potential energy of a system of point charges. Here, in the first case, expression for potential energy due to a system of 2-point charges in the absence of electric field. This is the first case, expression for potential energy due to a system of 2-point charges in the absence of electric field. Now I consider 2-point charges. Consider 2-point charges at point A and B. This is the point A and point B. Consider 2-point charges. Point charge Q1 at point A and point charge Q2 at point B. The distance between these 2-point charges is R from 1 to 2. R is the distance between 2-point charges from 1 to 2 means point charge 1 to point charge 2. Due to these 2-point charges, the electric potential energy, there is no electric field, there is no initial electric field at point A and at point B. But here, the amount of work done in bringing a unit positive charge or amount of work done to move a unit positive charge from one point to another point, this energy is stored as a electrical energy or electrostatic potential energy in this system. Here, consider two systems Q1 and Q2. These Q1 and Q2 are the 2-point charges at the points A and B. R is the distance between these 2-point charges. Here, the amount of work done or the work done to move Q1 from infinity to A. The work done to move Q1 from infinity to A. There is no initial electric field. We know the simple form. The electrostatic potential energy or electric potential energy P is equal to W divided by Q. The work done W is equal to Q into V or V into Q. In this case, the work done to move Q1 from infinity to A, there is no initial electric field. That's why the work done W is equal to 0. This is equation number 1. Here W1 is equal to 0. There is no initial electric field. Then the work done is 0. In the second case, here the work done to move Q2 from infinity to B. The work done to move Q2 from infinity to B. The amount of work done to move Q2 from infinity to B is, that is, work done W2 is equal to V1 into Q2. This is equation number 2. W2 is equal to V1 into Q2. V1 means where? Here this is the V1. Where? V1 is the electric potential at point B due to the charge Q1. V1 is the electric potential at point B due to the charge Q1. But in this case, there is no electric potential. There is no electric potential. Here, the work done to move Q2 from infinity to this point B, that is W2 is equal to V1 into Q2. Here, V1 is electric potential at point B due to the charge Q1. Then we get W2 is equal to V1 into Q2. Here V1 is electric potential at point B due to the charge Q1. We know the simple form or simple equation. Electric potential due to the system of point charge, that is V1 is equal to 1 divided by 4 5 epsilon naught Q1 divided by R12, which is the expression for electric potential equation due to the system of point charge. Now substitute this value in this equation. We get W2 is equal to, that is V1 is equal to 1 divided by 4 5 epsilon naught Q1 into Q2 divided by R12. This is equation number 3. Now we get the work done to move Q1 from infinity to point A and work done to move Q2 from infinity to point B. This work done is stored as electric potential energy or electrostatic potential energy. Here, now we get W1 and W2. We know the form that work done is equal to electrostatic potential energy U. Now, expression for potential energy due to the system of 2 point charges. That is U is equal to W1 plus W2. Substitute the values of W1 and W2 here. W1 is equal to 0 and W2 is equal to 1 divided by 4 5 epsilon naught Q1 into Q2 divided by R12. We get the equation. The electrostatic potential energy due to the system of 2 point charges in the absence of electric field, that is U is equal to 1 divided by 4 5 epsilon naught Q1 into Q2 divided by R12. Q1 into Q2 divided by R12, which is the desired equation for or expression for potential energy due to the system of 2 point charges in the absence of electric field. Here, electrostatic potential energy means the amount of work done in bringing the point charges or the amount of work done to move the point charges to their respective locations from the point infinity. That is called the electrostatic potential energy, or the amount of work done to move a point charge from one point to another point. That work done is stored as electrostatic potential energy. In the first case, we will discuss here the potential energy due to the system of 2 point charges in the absence of electric field. Here, consider 2 point charges Q1 and Q2 at point A and B. R is the distance between 2 point charges, and the amount of work done move Q1 from infinity to point A, that is work done W1 is equal to 0 because there is no initial electric field. Here it is this case, we will study in this case in the absence of electric field. That's why W1 is equal to 0. Then work done to move from infinity Q2, work done to move Q2 from infinity to point B, that is W2 is equal to V1 into Q2. Here V1 is the electric potential at point B due to the charge Q1. V1 is the electric potential at point B due to the charge Q1. We get V1 is equal to 1 divided by 4 pi epsilon naught Q1 divided by R12, when you are substituting this value in this equation, you get work done to move Q2 from infinity to that point, that is 1 divided by 4 pi epsilon Q1 Q2 divided by R12. This work done is stored as electrostatic potential energy. W is equal to U. Then we get U is equal to 1 divided by 4 pi epsilon Q1 Q2 divided by R12, which is the expression for the potential energy due to the system of 2 point charges in the absence of electric field. In case of in the second case, we will discuss about the expression for potential energy due to a system of 3 point charges. Potential energy due to a system of 3 point charges in the absence of electric field. In the absence of electric field. Expression for potential energy due to a system of 3 point charges. System of 3 point charges in the absence of electric field. This is the second case. Here, we know that the formula potential energy due to the system of 2 point charges, that is U is equal to 1 divided by 4 pi epsilon naught Q1 into Q2 divided by R12. Q1 into Q2 divided by R12, which is the expression for potential energy due to the system of 2 point charges in the absence of electric field. In the second case, we will discuss about the potential energy due to the system of 3 point charges. Now I consider 3 point charges are located at the vertices of the triangle. Here, these are the 3 point charges. These 3 point charges are located at point A, B and C. At point A, the point charge Q1 is located. At point B, the point charge Q2 is located. And at point C, the point charge Q3 is located. Here, the point charges Q1 and Q2, these 2 point charges are separated by distance R1 and 2. Here, this is the Q3 is located. This is the third charge. The third charge is located at a point C. Here R12 is the distance between from point charge Q1 to Q2. Here at this point. Here R is the distance between from 2 to 3. The distance between Q3 to Q1 is, that is R31. But now I am going to calculate the potential energy due to the system of 3 point charges. We know the formula system of 2 point charges. But this system of 3 point charges is here at a point C. Work done to move Q3 from infinity to that point. Here the amount of work done, we know the formula here. The work done to move Q3 from infinity to C. Here at the third charge at a point C, the amount of work done. The work done to move Q3 from infinity to C. Q3 from infinity to C. Here W3 is equal to we know the formula. W3 is equal to, how to calculate the W3 here? Here W3 is equal to, we know the form V into Q3. W3 is equal to V into Q3. Here the work done to move Q3 from infinity to C. W3 is equal to V into Q3. V is the electric potential energy or electric potential at a point C due to the system of 2 point charges. Electric potential at a point C due to the system of these 2 point charges. Already we will discuss in the previous classes electrostatic potential energy due to the system of 2 point charges. That is here W3 is equal to 1 divided by 4 pi epsilon naught. W3 is equal to 1 divided by 4 pi epsilon naught. Here W3 is 1 divided by 4 pi epsilon. Here, V is the electric potential at a point C. V is the electric potential at a point C due to the charge Q1 from the distance R31 and due to the charge Q2 from the distance R23. Then here we substitute W3 is equal to 1 divided by 4 pi epsilon naught. 1 divided by 4 pi epsilon naught Q1 divided by R31 plus Q2 divided by R23. V is equal to V is the electric potential at a point C due to the charge Q1 from R31 and due to the charge Q2 from R23. Then we get the equation W3 is equal to 1 divided by 4 pi epsilon naught Q1 divided by R31 plus Q2 divided by R23 into Q3. Cross multiply this value, we get here W3 is equal to 1 divided by 4 pi epsilon naught. W3 is equal to 1 by 4 pi epsilon naught. Multiply this value, we get Q1 into Q3 divided by here Q1 into Q3 divided by R31 plus Q2 into Q3. See, Q2 into Q3 divided by R23 divided by R23. Here the work done to move Q3 to C from infinity. We get this equation. Here this is the work done at point C. But now I am going to calculate the potential energy for the 3-point charges or due to the 3-point charges. We know the formula. The potential energy U is equal to W1 plus W2. W1 plus W2 means the potential energy due to the system of 2-point charges. Already we know that equation. The potential energy due to the 2-point charges is 1 divided by 4 pi epsilon naught Q1 Q2 divided by R12. Here W1 plus W2 plus W3. Now substitute this value and this value in this equation. Here we get the potential energy due to the system of 3-point charges. W1 plus W2, that is 1 divided by 4 pi epsilon naught Q1 Q2 divided by R12. Here also 1 divided by 4 pi epsilon naught. It is a common term. 1 divided by 4 pi epsilon naught. And Q1 into Q2 divided by R12. Q1 into Q2 divided by R12 plus here Q2 into Q3 divided by R23 plus Q1 into Q3 divided by R31. Here U is equal to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R12 plus Q2 into Q3 divided by R23 plus Q2 into Q1 into Q3 divided by R31, which is the expression for electric potential energy or potential energy due to the system of 3-point charges in the absence of electric field. Here consider the 3-point charges at the vertices of triangle. We know the formula electric potential energy due to the system of 2-point charges. Using the system of 2-point charges in the absence of electric field, we get the electric potential energy due to the system of 3-point charges. Here at this point, the amount of work done to move a charge Q3 from infinity to at point C, that is W3 is equal to V into Q3. Here V is the electric potential. V is the electric potential at the point C due to the charge Q1 at a distance from R31 and charge Q2 at a distance R23. Here that is electric potential formula 1 by 4 pi epsilon naught Q1 divided by R31 plus Q2 divided by R23 into Q3. From using this equation, here we get W3 is equal to 1 divided by 4 pi epsilon naught Q1 into Q3 divided by R31 Q2 into Q3 divided by R23. When we are adding the potential energy of the system of 2-point charges and the work done due to at point C is, that is U is equal to W1 plus W2 plus W3. This is W3. Then we get the equation U is equal to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R12 plus Q2 Q3 divided by R23 plus Q1 into Q3 divided by R31, which is the expression for potential energy due to the system of 3-point charges in the absence of electric field, which is the expression for potential energy due to the system of 2-point charges in the absence of electric field. Okay, dear students, the next concept of your topic is potential energy in an external electric field. Before this concept, already I have discussed the potential energy due to the system of 2-point charges in the absence of external electric field due to the 2-point charges and 3-point charges. In the third case, we will discuss about the potential energy of a single charge in an external electric field. The potential energy of a single charge in an external electric field. Now I consider a single charge. This is the single charge. Due to this single charge, or here the electric potential is present at this point. But here potential energy of a single charge in an external electric field. The potential energy is stored. But when this potential energy is stored, when an amount of charge is moves from one point to another point, there is some amount of work done is there. That work done is stored as a potential energy. Now I consider here at this point the charge is Q. Test charge is Q. It is present at infinity. The amount of charge or the amount of work done in bringing this charge from infinity to this point against the direction of electric field. Against the direction of electric field. Initially at this point, here U is equal to value is 0. U equal to value is 0. And the charge is moved from this point to this point, or work done to bring a unit positive charge from infinity to this point against the direction of electric field. We know the formula P is equal to W divided by Q. P is equal to W divided by Q. Here some amount of work is done. P is equal to W divided by Q. Then that work done is equal to P into Q. Work done is equal to P into Q. But here this work done is stored as a potential energy. Then we get U is equal to P into Q, which is expression for potential energy of a single charge in an external electric field. U is equal to P into Q. U is equal to V into Q, which is the expression for potential energy of a single charge in an external electric field. This is the third case. The next concept is potential energy of the system of 2-point charges in the presence of external electric field. Now I consider 2-point charges. 2-point charges A and B. At these points here, the Q1 and Q2 are the 2-point charges. These 2-point charges are separated by distance R1 and 2. Here Q1 and the Q2 are the 2-point charges in the presence of external electric field. Then here P1 and P2 are the electric potentials due to the external electric field or presence at a distance R. Now, initially we assume that these 2-point charges are present in the infinity. Now, the amount of work done to move that charge particles Q1 and Q2 from infinity to these electric potential P1 and P2 at point A and P. In the first case, the amount of work done in bringing a charge Q1 from infinity to where the electric potential is present against the direction of electric field, that is W1 is equal to P1 into Q1. This is equation number 1. In the second case, the amount of work done to bring a charge Q2 from infinity to where the electric potential P2 is there at that point P, that is W2 is equal to P2 into Q2. This is equation number 2. Then the amount of work done to bring a charge Q2 against the direction of electric field Q1. The amount of work done to bring a charge Q2 against the direction of electric field Q1, that is W3 is equal to 1 divided by 4 5 epsilon naught Q1 and Q2 divided by R12. This is equation number 3. According to the principle of superposition, superposition, work done at Q2, the work done at Q2, or here the total amount of work done at Q2 is due to two electric fields, that is W4 is equal to the total amount of work done according to the principle of superposition. The total amount of presence at Q2 is due to the two electric fields, that is W4 is equal to V2 and Q2 plus 1 divided by 4 5 epsilon naught Q1 into Q2 divided by R12. Hence, the total amount of work done due to the 2-point charges in an external electric field is equal to, or the total potential energy of the 2-point charges. The potential energy of the 2-point charges in an external electric field is equal to work done assembling by that configuration. Finally, we arrive at the equation, that is U is equal to here the total potential energy due to the 2-point charges in the presence of external electric field is equal to work done by the total work done assembling due to that configuration, that is U is equal to Q1 into V1 plus Q2 into V2 plus 1 divided by 4 5 epsilon naught. 1 divided by 4 5 epsilon naught Q1 into Q2 divided by R12, which is the expression for the potential energy due to the system of 2-point charges in the presence of external electric field. Up to here, we will study in this class external potential energy or electrostatic potential energy due to the system of point charges. In the first case, we will study the potential energy due to the system of 2-point charges in the absence of electric field. In the second case, already I have discussed the potential energy due to the system of 3-point charges in the absence of electric field. In the third case, potential energy of a single charge in an external electric field. Here in the fourth case, potential energy of a system of 2-point charges in the presence of external electric field. This is about electric potential energy due to the system of point charges. Thank you.